On the night of October 25th to 26th, 2025, a dam and reservoir in Belgorod near the Kharkiv border was hit. Regional authorities declared a state of emergency, ordered downstream evacuations, and warned of fast-rising flood risk. Roads that feed the front turned uncertain, bridge approaches grew risky, and supply crews froze as the river began to rewrite the map. This was not just cracked concrete. It was a strike at the bloodstream of the war, where a small shift in water can stall a long chain of trucks. If confirmed, terrain becomes a weapon, minutes become targets, and logistics can fail before battle lines even move. The question is sharp and simple. Who holds the river tonight? The units on its banks, or the planners who made the river move? Stay with military force for clear maps, straight numbers, and field-level analysis without noise. Like, share, and subscribe so you don't miss the full breakdown next. The strike hit a dam reservoir complex that sits behind the front, close to bridge approaches and fuel ammo staging yards. Local authorities moved fast. As emergency sirens sounded, phone alerts went out, and downstream neighborhoods received clear orders to evacuate. Police and civil defense closed riverbank roads, posted high-visibility barriers at low crossings, and warned drivers to avoid culverts prone to sudden surges. Engineers flagged weak points near bridge abutments because fast water scours soil, undercuts slabs, and turns small cracks into serious failures. Traffic controllers set one-way corridors for outbound civilians, while convoys supplying the front were told to hold in safe laybys. Town halls opened shelters in schools and sports centers, and they stocked water, blankets, and basic medicine for overnight stays. Field hospitals placed mobile teams on standby, since flood victims often suffer hypothermia, sprains, and contaminated water exposure. River gauges showed hour-by-hour jumps, which suggested a pulsing flow, not a steady release, and that pattern raised risk for temporary bridges. Hydraulic shock can break road shoulders where asphalt meets fill, so road crews marked shoulders with cones and kept heavy trucks off them. Drone footage from local responders showed eddies hitting key walls, which means pressure can push debris into pump intakes and choke them. Utility workers cut power to a few riverside blocks to prevent short circuits, and crews inspected substations for waterline creep. Rail operators slowed trains over causeways because ballast softens when saturated, and fast braking on wet rail can cause wheel flats. Logistics officers relocated diesel bladders and ammo pallets to higher ground, then logged serials to avoid losses during rapid moves. Fuel bowsers were lined up nose out for quick departure, and fire trucks patrolled with foam in case floating oil ignited. Radio nets briefly stuttered as masts took wind and spray, so backup repeaters and vans maintained command links across the corridor. Bridge guards measured deflection on temporary spans, since rising load and vibration can combine with water uplift to exceed safe limits. Bulldozers scraped silt from ramp entries because fine mud turns steel tracks and tires into skates, and that ruins momentum on climbs. Residents filmed water lapping at parking lots, and those clips, once geolocated, helped planners refine maps of probable flood spread. Meteorology teams tracked rain bands and upstream inflow, because a short cloudburst can turn a stressed river into a brown wall. Public briefings stayed calm and specific, listing street names, shelter hours, and hotline numbers, which keeps rumors from outrunning facts. Command posts shared a single picture across civil and military channels, so orders did not conflict and resources did not overlap. Buses with priority lanes carried seniors and children first, while vans moved pets and essential documents in sealed boxes. Ambulances routed around saturated underpasses, as pooled water hides potholes and risks axle damage that takes vehicles out for days. Checkpoint officers logged plate numbers at exits, which speeds re-entry and prevents theft in neighborhoods left without power. Crews erected portable floodgates at shopfronts, and hardware stores distributed sandbags with simple diagrams for proper stacking. Night lighting was aimed downward to avoid blinding drivers, and reflective tape marked edges where guardrails were missing. Every step showed the same logic, because safety buys time, and time keeps pressure away from people and critical nodes. With civilians moving and roads stabilized, the next question is how the attack was executed and why air defenses were fooled. The operation follows a clear kill chain built on speed, deception, and precision. Recon drones find the target, decoys bend the air defense gaze, and guided rockets finish the job. The goal is simple yet hard to block, because timing compresses choices before defenses can react. This chain targets the structure, not the crowd, and aims to break the logistics rhythm. That is how a local hit can grow into a theater-level problem within hours. With the logic set, the first step is eyes on the ground from the sky. Infrared reconnaissance. UAVs scan for heat, clusters that match fuel bladders, generator sheds, and truck parks. Thermal contrast stands out at night, so engines, power rooms, and cable rooms glow in clear bands. Operators cross-check hotspots with fixed markers and river geometry to avoid false positives. GPS tags help, but crews also use visual features, such as ramps and key edges, for geolocation. Target folders add angles, heights, and approach lanes for later weapons, which shortens decision time. A short dwell over the site limits exposure, because loitering invites counter-UAV fires and jammers. When coordinates are firm, the chain shifts from sensing to shaping the defender's picture. That is where decoys turn confusion into time, and time into a safe corridor. Low-cost UAVs act as false cruise missiles by spoofing radar cross-section, flight speed, and heat bloom. Simple RF modules can mimic seeker chatter, which tempts tracking radars to lock and follow a phantom. When batteries like 96L6E and Pantsir pivot toward the false vector, real gaps open at low altitude. The decoy path often sits just high enough to look like a classic threat profile. That profile is familiar to operators, so doctrine supports an automatic or semi-automatic response. Every second spent on the phantom pushes reloads and sensor focus away from the real lane. If a battery enters a reload window, even a short one, interception options shrink fast. This window is small, but it is large enough when rockets enter the final miles. From shaping the picture, the chain moves to the strike that matters most. Guided rockets with mid-range reach use inertial navigation and terrain reference to fly very low. Low flight cuts radar line of sight, while stable guidance holds the impact geometry. Near perpendicular angles maximize penetration on crests, abutments, or valve housings that bear the load. A compact charge with a hardened case can spall concrete and damage steel cores. Multiple hits along a tight band amplify cracks and push water pressure into fresh seams. This method values accuracy over volume because 6 good strikes can outweigh 60 weak ones. Technical claims about exact angles, warhead types, or GNSS cutoffs need cross-checks before citing numbers. Analysts compare drone video, blast signatures, and debris fields to validate any fine detail. What matters operationally is the effect chain, since structure loss forces rapid changes downstream. When structure changes, logistics routes wobble, and rear echelons pause under new constraints. That pause is the real target, because stalled resupply weakens units faster than lost vehicles. Once the strike lands, the story moves from fire to water and from steel to mud. With the chain complete, attention turns to how flood pulses disrupt bridges, roads, and staging yards. Flood pulses hit staging yards first, washing over parking lines, cab floors, and pallet stacks that sit on low gravel pads. Fuel bladders were shifted uphill in a hurry, yet hose runs stayed long and messy, which slowed pump cycles and raised spill risk. Command tents and radio awnings faced spray and grit, so crews sealed racks with plastic and moved batteries to dry crates. Every small delay compounded into slower turnarounds for frontline runs, which is how water turns minutes into missed windows. That is why the river now sets the pace of the fight. Bridge approaches took the next blow because silt gathers at ramps and turns firm soil into grease under steel tracks and tires. Engineers scraped the sludge with dozers, then laid mats to stiffen the climb, but heavy axles still lost traction under load. Traffic directors cut one lane on several crossings to reduce sway, which halved throughput during the busiest hours of resupply. Convoys idled with engines on to keep alternators dry and brakes warm, yet idling burned fuel earmarked for guns and generators. This is how a narrow ramp becomes a bottleneck for an entire sector. Temporary bridges on shallow piers faced uplift and side pressure, so guards read deflection gauges and enforced strict axle spacing. When readings crossed caution lines, units marked spans as unsafe for heavy, which forced rerouting to pontoon points downstream. Pontoon crews worked under strain, since setup needs calm water and clear banks, and neither condition holds during a flood pulse. Each crossing took longer than planned, and each delay pushed schedules for ammo drops and casualty backhauls out of sync. So the map did not change on paper, but time folded in the field. Air corridors carried some of the weight, yet airlift is thin when low clouds and jamming sit over the route. Helicopters can sling crates to forward strips, although sling loads invite small arms fire when approach lanes are predictable. Fixed-wing sorties want longer surfaces and cleaner weather, which are rare near a wet riverbank full of debris and mist. Every ton moved by air saves a unit for a few hours, but the numbers never match what trucks can deliver in steady weather. This is why air helps the symptoms while ground fixes the cause. Artillery lines reported irregular fire rhythms because shells and charges arrived late and in mixed batches. Crews conserved propellant, skipped non-essential missions, and waited for fresh fuses to match lots, which slowed counter-battery work. Maintenance pits lacked certain spares for breach seals and recoil fluids, so repairs stretched into the next cycle. Guns still fired, but the cadence lost its drumbeat, and that loss shows first in contested sectors around Vovchansk and Lyman. Here, tempo falls before territory does. Armor parks near the tree line also felt the drag, since wet ground traps recovery trucks and complicates track swaps. Electrics hate moisture, so connectors got fresh grease, and hulls ran with open hatches to vent mist after night moves. Field welders raised skids under tool chests to keep grinders and torches clean, which saved hours on basic fixes. Even small victories cost energy, and energy spent on drying steel does not move fuel and shells forward. Thus, attrition grows without a single shot. Rear echelons tried to regain rhythm with staggered dispatch, lighter loads, and tighter radio checks on choke points. Those steps reduced jams at ramps and kept bridges from stalling under mixed convoys. Yet each safeguard shaves capacity, and capacity is the currency of every front. So long as flood pulses recur, the defender pays in time, and time is the one resource the frontline cannot borrow twice. Open source evidence matters because pictures, pixels, and timestamps turn claims into facts. First, viral clips and early satellite tiles show water standing in yards, vehicles shifted from parking lines, and wet scars on warehouse lots. These images are useful, yet cloud cover, low sun angles, and compression artifacts limit how much damage can be measured from a frame. Analysts begin by confirming place and time, since a correct map pin and a clean clock are the base of every judgment. Geolocation uses fixed features like bridge spans, key edges, billboard poles, and roof patterns to match video frames to terrain. Landmarks must align in scale and angle, so cross-street distances and shoreline curves are checked against open maps and elevation data. Timestamping comes from EXIF fields when available, but shadows, weather logs, and power outage reports help when metadata is missing. Shadow direction and length can bound the hour, while rain radar and wind records anchor a plausible window for each clip. For flooding, before-after pairs are key, so teams compare older tiles with new passes from the same orbit to reduce geometry errors. Synthetic aperture. Radar is valuable because radar sees through clouds and reads surface roughness, which changes when water spreads over roads. Infrared helps at night by highlighting warm engines, transformer rooms, and power sheds, which signal activity inside soaked compounds. To avoid false positives, analysts cross-check thermal hotspots with known heat sources, such as bakeries, kilns, or district heating vents. Crowd videos are sifted with care, since duplicate uploads, mirrored views, and edits can distort scale or hide context. Each clip is traced back to a first poster, and the uploader's history is reviewed to gauge credibility and local presence. Audio is not ignored, because engine notes, sirens, and rotor beats reveal type and range when matched with known patterns. Water speed is estimated from drift of floating debris across known spans, then compared with river gauge readings and hydraulic models. These models use upstream inflow and slope to project pulse timing, which helps decide if a clip shows peak flow or a later backwash. Unit standards must be clean, so teams convert gallons to cubic meters and miles per hour to meters per second to prevent math slips. Damage scoring favors observable effects, like ponding on access roads, tilted light poles, and mud lines on walls, instead of raw guesses. Vehicle status is tagged by position and condition, for example, afloat, bogged, or relocated, which supports supply chain estimates. Warehouse impact is rated by roof staining, door warp, and skid marks near loading bays, which hint at water depth and cleanup time. Rail imagery is checked for ballast washout and track shine, since dull rails can signal low traffic and support claims of disruption. Power reliability is inferred from nighttime light patterns, voltage flicker and security feeds, and reports from local repair crews. False claims are pruned by hunting for mismatched flora, wrong license formats, or seasonal cues that do not fit October along this river. Confidence levels are then graded, high, medium, or low, so readers know which calls rest on hard geometry and which need more data. Finally, all layers are fused into one operational picture. Flooded yards, slow ramps, weak spans, and broken rhythms in resupply. That fused picture sets the stage for analysis of intent and payoff, because verified effects tell us whether the method is cost-effective or only dramatic. With the evidence weighed and the noise filtered, the discussion can shift to precedent and cost effect, where strategy meets the bill. Strikes on water infrastructure fit a long playbook where the real target is mobility, not masonry. Armies have hit bridges, piers, locks, and embankments to raise the price of every mile, because a broken crossing multiplies delay far beyond the blast site. A dam or levee adds a terrain shift to that logic, since pulses of water reshape ramps, roads, and rails at the same time. This method turns the river from an obstacle into a moving weapon, and that change forces the defender to spend time, fuel, and manpower just to stand still. From that angle, the goal is not destruction for its own sake, but disruption that costs more each hour it lasts, which sets up the cost curve for the rest of the fight. Cost effect favors short-range and mid-range systems paired with cheap UAVs, because small budgets can hit big vulnerabilities when timing and angles are right. A decoy that costs thousands can pull a battery worth millions, and that trade buys a few critical minutes for guided rockets to arrive clean. A rocket with a hardened nose does not need a huge charge if the angle is near perpendicular and the impact line hits a load-bearing seam. Multiple precise hits in a narrow band do the work of a larger volley, since stress and water pressure finish what explosives began. Under that math, dollars turn into minutes, and minutes turn into broken schedules, which is where advantage compounds for the attacker. The defender pays through forced choices, because every safeguard trims capacity while also burning resources. Cordon lines around risky spans slow convoys, while extra spacing cuts throughput by design. Pontoon bridges demand calm banks and security screens, and those screens tie down air defense teams that were meant for the front. Airlift can patch gaps for a day, yet weather, jamming, and runway limits keep tonnage small and predictable. Each workaround buys safety at the price of speed, which means the ledger bleeds time even when the map does not move. Analysts judge success by effect chains, not only by footage of damage, since the logistics rhythm is the real scoreboard. Indicators include hours lost per crossing, fuel burned while idling, and the share of sorties diverted to resupply instead of strike. Depot cleanup time matters, because wet pallets and ruined seals delay guns as much as lost trucks do. Repair cycles for bridge decks, river ramps, and culverts set the tempo for the week, while shored redeployments expose seams elsewhere. These numbers tell whether the strike was cost-effective or just dramatic, and they point toward the likely answer on the Vovchansk-Lyman axis. Precedent also warns against overreach, so the attacker must balance effect with escalation and confirm details before claiming totals. Flood pulses can be brief, sediment can settle fast, and a prepared engineer regiment can restore partial flow in days. That is why claims on volume, discharge, or permanent change should use clean units and cautious ranges. If disruption repeats along multiple choke points, however, the curve bends in favor of persistent pressure at low cost. In that scenario, the side that spends less to shave minutes will shape the next week of fighting, because time saved at the river buys freedom at the front. The lesson is clear. Control of terrain and minutes now decides more than raw firepower. Flood pulses, strained bridges, and slower ramps show how a precise strike can bend the whole supply chain. When logistics stumble, artillery cadence breaks, armored repairs lag, and frontline choices narrow fast. If the UAV plus rocket pattern repeats across levees, pontoon sites, and river abutments, disruptions will come in waves, not one-offs. The outcome in the next week will depend on 3 visible signals that anyone can track. Count how many pontoon crossings stay open for long, continuous windows without forced pauses. Watch the fuel and shell flow reaching forward units every 12 hours, because steady rhythm is survival. Measure shore density along the river, since more launchers on the banks mean fewer gaps for decoys and low flyers. These indicators tell whether the river remains a weapon or returns to a borderline. Stay with the military force for clear maps, straight numbers, and field-level analysis. Like, share, and subscribe to Military Force so you do not miss the next update.